Hello, my name is Raymond Panneton. I'm a professor at the University of Sherbrooke, and I'm also co-founder and vice president of Mecanum. Well, modeling poro-elastic material. In fact, I started with the modeling of porous material during my PhD at the University of Sherbrooke. So it was the goal at that time was to have a first numerical model for poro-elastic materials with a view to model acoustic problem like in an aircraft, where we have structural parts and also poro-elastic parts that are the acoustic part of the structures. And so at that time the modeling was analytical, simple models exist, but no complex model for real complex structure was existing at that time. The guys in the industry, the engineers, was trying to model these materials or the multi-layer material with this type of poro-elastic material that are included, and they were not able to feed the software because nobody knows how to obtain these 5 properties. So they call their manufacturer, the providers of the materials. Even the provider, the manufacturer was not able to give them the properties. So and then they come back to us because we were the modeler at the beginning, the one that proposed this type of modeling. So they came back to us and asked us, how do we feed this software? The poro-elastic materials, to model these materials, we need 9 properties. We have also Young's modulus, Poisson's ratio, the loss factor, which are the elastic properties of the poro-elastic material. But we need also 5 other parameters, 6 with the density. But the other 5 parameters are parameters that nobody knows at that time how to obtain them with a view to feed the software to have a simulation. Okay, so and these properties are the porosity of the material, and what we call the porosity is the open porosity of the material. Okay, if we take a foam, for instance, this is the open parts of the foam. Okay, so we have also what we call the resistivity. Okay, the airflow resistivity, it's kind of the inverse of the permeability to airflow. We have also the tortuosity. Tortuosity is the complex path of the waves when the waves travel through the materials. This is a parameter that accounts for it. And we have also 2 other parameters that we call the characteristic length. We have one for the viscous part and one for the thermal part. And those 2 characteristic lengths will characterize the loss of, in terms of viscous loss and thermal loss at higher frequency. So at that time we started a new project, a new research project on the characterization of materials. So of course we started with a literature review. We have found that in the acoustic literature some of the properties some methods for characterizing these properties were existing, not perfect. Sometimes it was quite difficult to obtain these properties with some type of ultrasound techniques, but anyway, we just reviewed these techniques, and when they were complex or when they were not existing, so we developed new methods for characterizing these properties. ASTM standards or ISO standards, so that we want to develop methods that are not just our method, but methods that can be under certain standards. Okay, so that people in the industry, whether they are in America or in China or in Europe, so they can use the same method, okay, with the same standards rule, okay, to make a characterization. I would say that all the theory, all the scientific work have been done at the University of Sherbrooke, where I am professor, but all the technological transfer, how to make these right research, let's say, okay, in terms of a product, so that the engineer in the industry can use it. So has been done in Mecanum. And Mecanum was kind of a spin-off of the University of Sherbrooke. okay, to transfer technologies that was developed for the acoustic weather modeling or acoustic characterization. So it was in 1988. Okay, so Mecanum has been a spin-off of the university. So we were able in Mecanum to manufacture this type of characterization equipment to support and develop the software. We have Nova software, which is the simulation tool for modeling the acoustics of multi-layer panels. And we have also FoamX, which is another software that has been developed for the characterization of the properties of the material. FoamX is a software that is used to replace, okay, some of our characterization equipments, because we can measure directly a parameter, okay, or with a specific equipment. Let's say I want to measure the porosity or the resistivity, okay, then I will need a porosity meter, I will need resistivity meter, okay, and if I want to use the other properties, I will need a system, a mechanical system for measuring each of the properties. Okay, so I need, let's say, 5 equipments. It's expensive, but it's very nice because it's direct measurement, so I have the real parameter. But sometimes some research center, some company have a limited amount to put on the acoustic, on their acoustic lab. So they want a solution which is not that expensive than having a whole laboratories of equipment. So we have developed this software FoamX, which is based on an impedance tube measurement. And an impedance tube is very classical in an acoustic lab. Probably every company that's dealing with acoustic material have an impedance tube. So they can use their impedance tube, make some acoustic measurement, like sound absorption measurement, and with the sound absorption measurement and the acoustic impedance that are measured on this impedance tube, so we can use these measurements with an inverse technique where we can have, by inverse method, the parameters of the material: porosity, flow resistivity, tortuosity, characteristic length, and also the elastic properties. Okay. So we can have a solution which is based only on an impedance tube and inverse techniques that can characterize all the parameters of the poro-elastic materials. At the beginning, we developed Nova as a standalone application to simulate the acoustic properties of a multi-layer panel. Okay? And when I'm talking about multi-layer panel, I'm talking about a typical panel that we can find in a car, an aircraft, where we have combination of elastic panels like a steel plate, aluminum plate, with air gaps, with poro-elastic material. And then we want to be able to model this to have at the end a prediction of the efficiency in terms of sound absorption, sound transmission, or other acoustic properties. And then, well, this is a standalone application only for multi-layer panel, okay? And it's simple, okay? We cannot simulate complex structures like an aircraft, okay, or a car, but with a view to be able to predict the efficiency of a panel in a given environment like an aircraft or a car, we need to combine Nova with more complex software. Okay, and this is where we've been working with the ESI to have this combination of Nova for characterizing the properties, the acoustic properties of a multi-layer structure, and ESI with the VA1, okay, with the VA1 software, where they can model the whole aircraft, for instance, okay. But on the aircraft, okay, we have panels, and the panels are characterized by Nova. So combining both, okay, we can have at the end a very nice solution to be able to predict what is the sound, the sound pressure inside the cabin of an aircraft, for instance. So we have used NOVA to characterize different type of multi-layer structures that we can find in a car, for instance. We have the dash panel of a car, the door of a car. All of these parts are multi-layer structures. We have used it also to design a sound enclosure, okay, to have a very high sound transmission loss at STC. We have used NOVA to simulate also the sound transmission of wall in a building. Okay, the wall in a building is a very typical structure where we find an elastic wall, okay, an air gap, so we have air between walls, and then we have also porous material like the fiberglass. For now, with all these simulations tools, for the last 15 years, okay, we have made a lot of simulation, we have optimized, we have done some research on the optimization of porous material in terms of sound absorption, sound transmission, and we have reached a limit with what we call conventional material, okay? So we can have a single layer material, multi-layer material, but all these materials are always with conventional material. Aluminum panel with a fiberglass, for instance, or rock wool, or polyurethane foam, and they have kind of a limit that we need to go over now. Okay, we have to go to some higher properties in terms of sound absorption, sound transmission. So the trend now is to go to master what's happening at the micro scale. Okay, the physics, not of the material itself at the macroscopic scale, but at the microscopic level. Okay, so we go in the material, try to optimize the cells, try to optimize the fiber structures for fibrous material to have a better sound dissipation in the material by better understanding what's going on at the micro scale. And then we can generate some microstructures, okay? And sometimes these microstructures are not those that are obtained by natural process, okay? And sometimes when it is not obtained by natural processes, we call these materials meta material, where meta stands for superior, okay? Which not come from the nature. We are designing the new microstructures by hand, okay? So that we can reach the optimal sound absorption, the optimal sound transmission. And these are the trends, okay, that not only us, but many researchers, many companies in the world are investigating now. Okay, we have collaboration with large companies in the aircraft industries where they are involved, okay, in the design of meta materials for acoustic application. We call these materials meta-acoustic material, okay, and these are big companies now that dealing with these materials, and they want to have these new materials to challenge the low frequency noise in the aircraft, for instance, okay, because low frequency is always a big challenge because it's a large wavelength and we have limited thickness, okay, and we have to deal with small thickness with low weight when we're talking about aircraft application, and so all these limitation goes in the other ways than acoustic needs. Okay, usually we need heavy things, we need large thickness, but now it's the contrary. We need to go thinner, we need to go at a lower density. Okay, and then the only solution for now that seems to be a very interesting research path is the metamaterial. So we have already some solutions that we can find in the literature, even on the market, okay, where we can see new materials which are very thin. We're talking about, let's say, 20 millimeter thick, okay, less than 1 inch. So we can have 100% of absorption at 300 hertz, okay? But they are structured material. For now, it's man-made, okay? It's using 3D prototyping, It's not at the, let's say, TRL level of 7 or 9. Okay, we are at lower TRL for now. We need to have validated this to be sure that it will be commercially viable, okay, before we can think about manufacturing for having a product with that. So, but this is where we are now. We try to have a process. We're talking with companies that manufacture these type of materials, well, classical, conventional material, and we're working with them to implement in these materials this type of meta technologies that we can have at the end, very thin material with a very high absorption or sound transmission efficiency.